Welcome everyone to the Ontology Summit 2021. Today is the 17th of March, 2021, and this session is in track B, which is on definitions. And I'm very pleased to introduce our first speaker today, who is Selja Seppälä, who comes to us from University College Cork, Ireland. She's the Marie Sklodowska-Curie Career FIT Fellow. And she'll be speaking today on systematizing definitions in ontology. So, Selja, go ahead.
You can, okay, so, see, share, and then do this. Can you see the slides?
Yep, looks great.
Yes.
Perfect. So, in this talk, I will present a method, well, a proposal of a method to systematize definitions in ontologies. And so the idea is to show how this method can simplify and accelerate the definition writing process. But first, I want to give some background to point out some characteristics of definitions that are relevant for the rest of the presentation. Here's an example of a definition from the Ontology of Medically Related Social Entities. It's the definition for hospital function. And as you can see in this next slide, a definition of this sort has an internal structure, so a definitional structure composed of features, pieces of information about the defined thing. And the canonical definition structure has a genus which categorizes the defined thing under a more general type. And a canonical definition would have one or more differentia that distinguishes the defined thing from the genus's referent and from all the other things that fall under the same type. Moreover, a definition also has a semantic structure where each feature expresses some type of relationship between the defined thing and other things. So in this example, we can see that this is represented as relations here in the example between the defined thing and the defined class hospital function and other general upper level classes in this example. So we have a function, so hospital function is a function, hospital function, it inheres in some material entity and it's realized in some process. A definition is only one type of knowledge representation among several possible ones. So as we can see in this example, axioms also express, that represent facts about, so knowledge about the thing we are defining or the thing that represents, the class is representing. You could have a graph, so these are different forms of output with different levels of expressivity. So definitions, the axioms would be the logical definition used in ontology, and the textual definitions would be the counterpart for human users. So the method that I will outline now illustrates how to create templates for textual and logical definitions, starting from one or more textual definitions. So let's say we have this definition of hospital function. the first step of the method consists in identifying the definitional structure in terms of genus and differentia of this definition. So here we have three elements. We have the genus, a function, and two differentia, inherent in a material entity and the realized by, etc. From here, the second step consists in identifying the type of things that we are defining. So we look at the genus and we say, okay, this genus, it's a function. So the function would be the relevant class in our ontology if we had a very general ontology.
Ça permettait de jeunes étudiants québécois.
And if let's say if we didn't have a relevant, let's say we were looking for hospital function, the class didn't exist in the ontology, we would go for a more general class, so a superordinate class. And if, let's say, there's no relevant superordinate class in our ontology, we would maybe, as here, for example, choose a class in an upper level ontology. And here in this example, I deliberately chose a very general class to show how this can be then specialized further, just for illustrative purposes. So once we have identified here the relevant class for our use case, the third step consists in creating a class template for this relevant class by listing all the axioms of the class, so its own axioms and the inherited ones. So we get this kind of little template for the class that we are interested in. So in this example, I took the class from function class from Buffo1 and listed some of the characteristics there. So once we have this class template, we can use it to describe, in the fourth step, describe the semantic structure of a definition, as we saw in the introductory slides. So here we look in the template, class template, which features would be helpful for describing the contents in the definition on the left. And we find that inheres describes, well, the first differentia, the content of the first differentia, and the second differentia would be expressing realized in process. But this template is still kind of underspecified, since the last part of the definition, the realized in process, contains more specific information that can also be analyzed in the same way as the whole definition. If I go back to this, here we can see that that is realized by the material entity at which inpatient, etc. There's more information in there. So basically we can go through the whole same process again. So we identify that we're talking about a process. We look up the category that we're interested in, the ontology. We create a mini class template for process here. And then in the same way, we analyze the content of this element with one of the features in the process template. So
let's see.
Yes.
Notice view options.
Sorry about that interruption.
Oh, yeah. So here, sorry, now I, okay, so yes, we were specializing further the template for this function here that we're describing here. And we specify this template further by adding some information about the participants to the process that realizes this function. So in the fifth step, we refine the class template, as I was saying here. So we get this function template that characterizes functions in this, or this kinds of functions is in this ontology. The issue here is that these classes and relations in this template might still be too general. So in this case, they don't apply to all functions within this ontology. And so, yeah, in this case, these inheres in material entity, realized in process, they're not specific to functions of hospitals and other architectural structures described in this Omer's ontology. So we can further specialize the template to fit the specific use cases we're interested in. And here we adapt a template to further distinguish functions inherent in buildings from functions inherent in persons, for example. And so using the classes in the ontology, there's a class architectural structure, of which hospital is hospital, well, the subclass is hospital, sorry, yeah, and healthcare encounter, there are subclasses of these in the ontology. So we refine the class template to fit our use case. And then now that we have this more specific template, class template, we can create templates for the textual and logical definitions. And for that, if there's already a textual definition, as we have in this example, you can take that and kind of see which parts correspond to placeholders that can be updated depending on the type of architectural structure we want to be defining, for example. And we create this textual template where architectural structure is a placeholder, and then you have a function inhering in a architectural structure, which is also a placeholder, and you can then specify that with lower level classes, etc. And you do the same thing for the axioms. And once you have these, so these definition templates, you can output the actual definitions for the lower level classes with using those templates. So, for example, using the architectural structure template, we can generate the definition for hospital function using subtypes of architectural structures that correspond to the hospital function. So here we have healthcare facility would be the architectural structure, and healthcare encounter is here replaced by a description of the encounter. Inpatient and outpatient healthcare is provided to a patient population, but it could be, so this is for the human readers, but then in the axioms, it would be healthcare encounter. And same thing for emergency department function. So you just replace with a lower level class all the placeholders. And so the output templates that I created here were used to generate both logical and textual definitions for emergency department function, which did not exist in the OMERS ontology at the time I did this. And the text in the last part of the textual definition, so at which urgent healthcare is provided to a patient population, was adapted from the original definition to match this definition that is kind of at the same level of specificity. And so to conclude, here's a summary of all the steps. And they appear here in the order I presented them, but this method is actually quite flexible, and it could start actually at either one of these steps, and you could start it from one textual definition or more, or from a logical definition or a set of logical definitions, and you can. So it's mostly like kind of the general idea of how to go about creating the templates if you have a textual definition or axioms. And in any case, wherever you start, you would most likely cover most of the steps. So yeah, at the end, the general idea is to use existing textual and or logical definitions to create templates that can be then reused to generate definitions. And I imagine this method is probably already used for creating ontology templates and ontology design patterns, as we saw a couple of weeks ago with Envo. But I thought it would be useful to make this kind of method explicit. And yeah, so as you can see, it's probably suited for automating definition generation processes that are used in these template design patterns, for example, ontology templates. And it should also be useful for definition checking, in particular, to ensure that textual and logical definitions contain the relevant information and that they're not too far apart from each other. And yeah, and in that way, it can also be used for quality control of the definitions and the ontology. And so to conclude, of course, this method might not be suitable in all cases, but it still has several advantages whenever it is applicable. So it's not only useful for systematizing and accelerating the creation of both textual and logical definitions by creating kind of recursively specifiable templates, but it also increases consistency of definitions and of ontologies in general. So thank you. And if you have any questions or comments, please, I am happy to answer. I'll stop sharing the screen now.
Thank you.
Find the buttons, stop share. Okay.
That was great. We'll get to the questions after all of the panelists have spoken.
Okay.
So I would like to move on then to Andrea, whose slides have been posted to the meeting webpage in case you want to review them. Andrea is a
sorry, go ahead.
He's a software and knowledge engineer and CTO of Onto Insights. And she'll be speaking on experiences with foundational domain and application ontologies in OWL2. Go ahead, Andrea.
Okay, I'm trying to share. Just let me know if my screen, you can see it.
Looks great, thank you.
Okay, so I really appreciated that first talk because I kind of line up with that and agree with a lot of things that were said. This is more a talk about experiences and stuff that I've done. And it actually came out of some email exchange I had with Alex, where we were talking about foundational domain and application ontologies. So I first wanted to start off with some experiences that I had with foundational and domain ontologies, which in which I was the member of a program that was trying to understand correlation, cause and effect relationships based on what was being observed in news articles and being extracted by NLP from research documents and stuff like that. Originally, the program was going to be solely based on using CERTIC's Common Core Ontology and TRADOC's Operational Environment Ontology. I think the TRADOC Ontology is actually on GitHub. Both of those are derived from BFO, so they both started from there. And as the program went along, for about 6 months, 3 of the different natural language extraction teams just struggled with how to encode different events in these even more specific domain ontologies, but even in the foundational ontology, how to capture their participants, how to understand locations and what they needed to convey. And it kind of was a disaster. Where the teams actually decided to publish triples, everyone chose different classification entities, different approaches for how to locate things or how to tie things together. And in the end, what we ended up doing was we really created a specific event-based ontology. And from my experiences on that, along with work that I had already done in NLP and natural language understanding, NLU, I kind of got very attracted to this linguistic theory of events and using events to help define ontologies. So interestingly enough, last year I found this paper that it was actually, well, 2 years ago now. I found it last year, but it was published 2 years ago from Science Direct. It's called Measuring Expert Performance at Manually Classifying Domain Entities Under Upper Ontology Classes, which is definitely a mouthful, but it actually dealt with BFO, and it seemed to have findings that reinforced my experiences on this previous project. And it kind of says, you know, even for a well-understood domain, and they picked travel, you know, they picked something that people could relate to, airplanes and going places and that sort of thing. The results of the manual classification was really inconsistent, which is the same thing we found on a much smaller scale. The mean agreement of the participants was only 51%. So that was kind of scary. And it kind of told me that, or informed me that trying to get people to take philosophical distinctions and classify according to philosophical distinctions was not very natural for people. So then, like I said, I really got tied into event and linguistic theory. And a lot of what I worked on is really going back to the 60s, where Davidson published a paper, and Wendler also in 67 published a paper that attempted to distinguish states versus events, but more importantly, reified events and states as individuals. So you could say things about events and states like they were individuals. And Wendler went farther, and then he decomposed events to things that have achievements, to things that have accomplishments, to things that are activities that have ongoing. So you get telicity involved in all of this. But these papers are very well cited, are pretty well known in the linguistic space. Bach came along in 81 and then said, let's use the term eventuality for both events and states, because there's a lot of things you can talk about that are both conditions or factors and events and things that are the same. So I kind of followed down that path for a while. And Fillmore also in 67 kind of created this whole basic semantic role labeling FrameNet architecture. So it kind of, the 60s was kind of really cool for all of this. And there's much more, and there's so much more that's been going on in linguistic theory and analysis and cognitive science too, related to events. So why events and narratives? Humans really aren't set up to understand logic. They do understand stories, from just being a little kid and reading, your Silly Sally, picture book to your children. You put together stories and you connect things together. In a story, just basic cognition divides a story up into events. And I put a couple of references to articles here, but producing narratives is not only an ability that's more or less natural, it's pretty natural, but it's a topology for how people store information, make sense of what's happening in the world, define cause and effect, and really use a story. Even cultures use story to explain what's happening in the world. So I kind of went along and said, well, I'm going to make, and this is kind of just me throwing out some ideas, and it started off in this project that I was on several years ago, semantics of events. And so you can kind of see down here, you have events, and some events cause other things, some events enable other things, some events prevent other things or states. You have processes that are sequences of events. They have starts, they have ends, they have nexts. Anything can have a component. We see has component up there. I use the word script for a narrative because basically some of the work that Onto Insights is doing with narrative is based on a script and then expanding out from that script. But if you really kind of think, and I'm going to just jump 2 slides ahead here, you're really answering the who, what, where, when, why, how kind of questions. And also start to bring in intent and possibility. And so what you see, if you go back up to here, is you have the when, you have the where, you have the what was done, you have the who. Definitely collections are always, it's kind of a very relevant thing. You group things together, but you can start to go down an OWL2 class of punning, or just label something as this is my generic entity, kind of like my husband got a Ford Raptor, and there's a generic Raptor, and then there's the Raptor he got with these different options on it, those kinds of things. A future event, those kinds of things, but provenance, where information came from, because a lot of times, even in news articles, there's still always a flavor of your natural, the author's leanings, their confirmation bias, their personal experiences that they bring to things. So very important to understand where something was sourced from, where you found it. Maybe it's in a spreadsheet, maybe it's in a document or something. So kind of provenance of where things were found, events that say, like John Smith said, Mary was pregnant or something, so who said things, you can start to say that that's an event, it's a communication event. But going farther and also thinking about definitions and human understanding and computer understanding for natural language processing. What are antonyms? What are synonyms? What's the definition of something? Can you give me some examples? Can you give me negative examples? How would a sentence be structured that involved an organization, maybe, or a bank, or, going back to the first presentation, a hospital. So those kinds of entities. And so this is where this whole top level ontology came from. But because nothing, no matter what you read, it may not be true. There's a probability of truth, and there's also the confidence that you have in how well it was defined. So I've kind of gone down this path of using RDF star, or graph properties, because it makes it lots easier than reification. Of course, you have to find a backing infrastructure that supports it, like I think GraphDB does, Stardog does. There's several, Neo4j does. There's several backing infrastructures that actually support RDF star, and I have come to very much value it. So there are ways to get around it if you're not using RDF star backing infrastructures, but which is just basic reification. But these concepts come in very handy. Just to make the who, what, where, when, why, how more explicit, the event state ontology that derives from that top level just kind of goes, so an event has a location, a state has an agent. A state can also, any event and state can have a location. There's agents involved. Who's an active agent, actively doing something, animated, what's an affected, who or what's an affected agent, providers, recipients, you can keep going. These are the instruments, you know. John wrote the book on his typewriter. Well, a typewriter is a resource. That's his instrument. Or an event and state has a topic of something. John rejected, or Mary rejected John's proposal of marriage. So a proposal of marriage is an event, and Mary's rejection of John's proposal is another kind of event, which, has the topic of that initial proposal. And then time is the when, and time being beginning and end. And this is very much a W3C concept of time, where you have points in times, intervals, durations, those kinds of things. But in addition, some of the ontology work that I've done has also created recurrence patterns and an understanding of seasons. Winter, spring, summer, fall. And even winter, spring, summer, fall there's common sense knowledge associated with those seasons, but there's also context associated with it. What's winter in the Northern Hemisphere is not winter in the Southern Hemisphere. So you kind of need to take all of that into consideration. I already discussed this slide. So how do you actually develop an ontology of events? I actually start from the verbs, not from the nouns, only because there are way fewer verbs than there are nouns. And if you start from nouns, you're never done. Understanding what's actually influencing the domain. So like even in a pizza ontology, because I know that Proteges, starts off with trying to teach people about ontologies with the pizza ontology, or you have the food and the wine ontology. But what really matters is not that you want to characterize all the foods and wines. You're characterizing them for a reason. What do I want to buy? What do I want to sell? What do I want to make in terms of a pizza? What do I want to drink in terms of a wine? What pizzas I want to eat, and when do I want to eat them? So really it's being influenced by these events, or the verbs, the things you are doing. And all the way back into the 90s, I really took more of a systems thinking approach to understanding your domain. I actually thought this book was pretty amazing, Gerald Weinberg's book. What's the purpose of trying to understand the domain? What's your domain? Okay, let me go here, try that. What's the functions that you're worrying about? What are the boundaries? What are your influences? What's the environment or context you're working in? What are the component parts you need to worry about? There's many more questions in a systems thinking approach, but it's a very practical approach to developing an ontology. In terms of definitions, you can kind of see some of my OWL2 definitions here. I'm very fond of Turtle because it's much more readable than anything else. But what are your subclasses? What are your domains and ranges? Creating definitions. So creating the diagrams is one thing that I do to help people understand. Creating the turtle is for computers and people. And then there are spreadsheets that I also automatically generate that help people who would find, you know, even turtle daunting. So put it in a spreadsheet. People are used to that. And this is another kind of approach that I've taken. I use Python a lot, and there are so many amazing libraries in Python that, you know, like will generate this. This is all computer, you know, generated just from Python libraries. Let's see. But even going farther, using logic and probabilities in OWL 2 is not impossible. Just plain old inference reasoning that you can do with RDFS, your subclassing hierarchy. So for example, if you're trying to determine if an area is subject to violence, look for acts of violence and find evidence. And that also comes into argumentation, which is my next slide. Or if I know my domains and range definitions, I can use them and then understand that an instance that has a count in it is automatically a collection. I don't have to define everything. I can infer other things from it, and it's a collection that has members in it. Even if I don't know explicitly who the members are, I know that they exist. Another step or an important piece of logic is what are your inconsistencies or contradictions that are in your ontologies? And can you repair them, or is it valuable to exclude them? In terms of splitting all your possible knowledge, all your instances into different groups, where maybe some rules and some conditions apply to some groups, but not to others. And once you've split your instances, does that make your analysis, your ontology consistent, or and your instances consistent, or does it not? So you can start to go down a path of really better understanding instances, really doing more complete analyses when you take your axioms, your definitions, your hypotheses into effect and potentially split your instance sets by various criteria in some way, just analyzing a population according to its attributes. Another thing I've done is to use Swirl, because I use Stardog a lot. I use Swirl, they have Swirl support, and capture relevant common sense rules. And two places that I get common sense rules from are the Atomic database and ConceptNet, which I supply the links there. And again, the use of probabilities and RDF edge properties. And lastly, I wanted to talk about argumentation, and because I want to wrap up real quickly. This is really, it started out for me with discovery of evidence for cause and effect. And your answers when you analyze evidence is, I see, or correlation, I see correlation, I see cause and effect, I don't see it, I really don't have enough data, it's totally unknown, or I have contradictory data and it's undecided, and I can present it to you, the user, and you can make a decision on what you want to do or potentially add more rules to the infrastructure. So another example would be to analyze events. Is there a competitive or a cooperative relationship between two individuals? Now, those could be countries, they could be, you know, organizations, they could be people. And what you then do is you look at what events are observed that regard those individuals, that in which the individuals participate, and then do those things support or refute an assumption of competition or an assumption of cooperation. And the really nice thing about this is that it gives you the benefit of explainability. You can say to somebody, to a user, I think that these two groups are in competition because I have this evidence. I also might have this refuting evidence. Your call, according to prioritization rules or whatever, the refuting evidence is less compelling than the supporting, perhaps. And going much further in analyzing narratives, which is where my real focus is right now, what events are discussed? Is there any consistency in, if you have a whole set of narratives, in the inclusion of specific events and certain types of narratives with certain outcomes? What sequences tend to lead to positive versus negative outcomes? What assertions can you make by analyzing these stories? And in different analyses, what weights do you want to give to different supporting versus conflicting events, i.e., the value of culture in some stories, or the value of location, taking context into effect, could change what weights you give to evidence, what weights you give to common sense rules, even, and that takes you down the path of defeasible knowledge. So that's my slide set, and I know we're waiting until till the end for questions. So thank you.
Thank you, Andrea. That was really insightful. So
And
now we move on to Caitlin Woods, who comes to us from the University of Western Australia. She'll be speaking on representing ontologies in natural language and first order logic. Why do we need both anyway? Caitlin?
All righty. So hi everyone, and welcome to my presentation on representing ontologies in natural language and first order logic. My name's Caitlin Woods, and as the introduction said, I'm from the University of Western Australia, and I'm presenting this presentation on behalf of myself and my colleague Emily Lowe, who couldn't be here tonight because it is currently 1 a.m. Where I am. In order to explain the contents of this presentation, I will first explain a little bit about who we are and the perspective that we come from. So we're members of the UWA System Health Lab. And when the System Health Lab was first created by Professor Melinda Hodkowitz, who is a maintenance engineer and has been a maintenance engineer for a long time, the purpose of the lab was to estimate the useful life of engineering equipment using data. But throughout the first few years of the lab, it became very clear that industrial data often resides in many different data sources. It's quite difficult to integrate and understand that data. So we created a sub-team of the System Health Lab who are focusing on industrial ontologies for maintenance. So over the last 3 to 4 years, we've been working on this and have been involved with the Industrial Ontologies Foundry Maintenance Working Group. And many of the thoughts and lessons learned that I'll present today have come from our own ontology projects and some of the work we've done with the IOF as well. All right, so since the System Health Lab comes from a maintenance engineering perspective, entering the formal ontology research community was kind of a slow process for us. And we found it really difficult to understand much of the terminology that was used in the training materials from the ontology community. Furthermore, it was really difficult for us to explain to the industry domain experts that we deal with very often why ontologies were really necessary for their data. So to combat this steep learning curve for engineers, we developed a blog called Ontologies Explained. And it focuses on explaining ontologies using examples that are relevant to people from the engineering community. So we deal with issues such as how to explain ontologies to your boss, right down to the nitty-gritty of how to create first-order logic descriptions. So throughout this presentation, that's what I'll be doing. I'll be using examples from the engineering domain, to demonstrate the real value of first order logic definitions for us. I will also discuss why this translation should be treated as a collaborative process and why that worked so well in our team. And I'll finish the presentation with just some lessons learned from our ontology projects. So hopefully this will be useful for you if you're, say, not familiar with the ontology community. I'm sure many people in this chat are, or trying to explain ontologies to someone or definitions to someone who's from a different community. So to explore how natural language and first order logic can be used to represent concepts in engineering data, let's start by looking at the concept of machine identifier. So this is a concept that's used widely in industry to identify equipment. The problem, however, is that in industry, it takes many different names and many different forms, such as asset ID and functional location. So having a unified concept for machine identifiers is an essential first step towards integration of many different industrial systems for asset-intensive organizations. So on this slide, there are 3 types of definitions. First, we have a subject matter expert definition. So these look like definitions you might find in international engineering standards or textbooks, dictionaries, etc. So the SME definition for machine identifier could be a unique identifier or serial number of a machine or asset. And these machines might be trucks, pumps, conveyors, etc. First order logic definitions are formal definitions that represent facts about their objects and attributes and relationships between them. So the first order logic definition for machine identifier looks a bit like this, and we've color coded that definition according to what part of the subject matter expert definition that it is referring to. So lastly, we have an English translation of a first order logic definition, and we found these incredibly important because only one person in our team was a logician. So in order to understand some of the first order logic definitions initially, we created direct English translations of these definitions. So this can really help when someone's not too familiar with first order logic. So for us, the reason that SME definitions need to be translated into first order logic is twofold. First, it transforms information into a format that computers can understand, in line with how the ontology will eventually be implemented in a machine interpretable language like RDF or OWL. And second, FOL definitions are generally more rigorous and precise than SME definitions, and therefore can allow the identification of more precise SME definitions. So essentially, this process is about improving the way the different parties in our engineering communities who deal with engineering data, who create the data, who use the data, all communicate with each other. So we're really talking about the same things in our data, and I'll explain a little bit more about this. So in the last slide, I said something very important, and that was that first order logic turns data into something that a computer can understand. And this is the key to why we need first order logic definitions. That is, it makes data machine readable. Currently, much engineering data is stored in non-uniform formats, such as PDFs in the case of procedures, or spreadsheets in a case for some risk analysis processes, such as the failure modes and effects analysis. And when digitalization projects have taken place, relational databases are often used to store data. These data sources can be integrated, but often this is a really costly process. And these efforts can be made much easier, cheaper, and more future-proof with the help of first order logic. So if we consider the definition for a failure mode. So in engineering, this is a standard code used to describe the type of failure that that a piece of equipment has experienced. For example, the code BRD could represent a breakdown. So the SME definition for this concept could be a code used to describe the failure of a maintainable item. If, say, a software developer wanted to build an application that includes failure modes, they would need to really understand what's meant by a failure, a maintainable item, and to describe. And now we can look at this from also a different perspective. So in industry, failure mode codes are often found across two different data sources in companies such as mining companies. The first is an Excel spreadsheet, which results from a failure modes and effects analysis. Now, failure modes and effects analysis is a process that engineers go through to try to predict what types of failures a machine or a piece of equipment could experience so that we can mitigate those risks. The second data source is work order data. So we have a technician out on site and they've noticed a problem with the equipment. That they will generate a work order so that that problem can be rectified, and that work order will have a failure mode code in it. So we can see in this illustrative example we have here that failure mode codes are often called different things and they're connected to different fields in different ways. So we have in our, for MIA, we have it called failure mode code, and in our relational database, it's just called code. So despite this data being in a digital format, the computer doesn't know what these entities are, how they're connected, or if they're the same as one another. Therefore, the integration between these sources is an expensive exercise requiring multiple domain experts. Now let's consider the first order logic definition for failure mode. So this definition states that a failure mode is a descriptive content entity, and there exists some failure mode that the code denotes. Mapping this first order logic definition to our existing data sources allow us, the data owners, to really interpret the meaning and the connections between the data. If this is translated to a machine interpretable language like OWL, we can begin to do automated reasoning, etc., over this data as well. All right, and the second point I mentioned, the second advantage, was that first order logic makes data more precise. So in the middle, we have an SME who's describing a functional location. And they've said a functional location is where a maintenance task is actioned. Now, on the right, we have someone who has come along and is trying to make a first order logic description and is trying to understand what this natural language description means. And they've interpreted that natural language description as a spatial region, which is the location of a maintenance task. However, someone else who might have been in industry for a long time and really have a deep knowledge of how functional locations work has described a functional location as a descriptive content entity that the maintenance task is, that describes where a maintenance task is actioned. And this is more reflective of how functional locations actually used in industry. So functional location is a description of where a piece of equipment sits in the asset hierarchy. In first order logic, it's good practice to state the immediate superclass of the concept you're describing. And this process really caused our two modelers to try and understand what that immediate superclass was. And we were able to identify a problem in the SME description because that description was interpreted in different ways. So why do we need natural language and first order logic? So something that might have come to your mind is, but surely we could just make our SME definitions more precise, and perhaps we can just be more descriptive straight off the bat. And if we have precise SME definitions, why do we need first order logic definitions too? And our perspective on that is that it's important to translate back and forth from first order logic to SME definitions as a iterative revision process of your definitions. So for this reason, we think that translation should be both an iterative and collaborative process. So this is our ontology team, and this is the makeup of our team. So obviously your team will probably look a little different to this, but I want to explain why these different skill sets really work for us when translating natural language to first order logic and then eventually into ontologies. So we have a subject matter expert who highlighted important domain specific maintenance concepts that we needed to model, clarified the interpretations of those concepts, and provided real world examples and counterexamples based on the definitions that we created. We were lucky enough to have a mathematician, philosopher, logician in our team who had a really sound understanding of how mathematical symbols string together into first order logic, and was able to perform the conversion from natural language definitions into the first order logic interpretations and vice versa. And finally, I am my background's in software engineering, and I'm now an ontology engineer. And I was able to take these first order logic definitions, link them to existing upper level ontologies like BFO, and prototype those first order logic definitions in OWL to check their consistency. So this was really a back and forth process between us three, where we went and we reevaluated our definitions over and over again until we came to something that we're all happy with. Another good thing is that we had these different skill sets, so we tended to really find different mistakes in these first order logic descriptions. And as I'll demonstrate in this slide, a mistake in a translation can really change the meaning of a definition. So say we have the SME definition for a machine identifier that we've seen before, and we've seen what we believe a correct translation of that to be. But if someone translated this incorrectly and did not include the fact that that identifier needed to be unique, that would really change the definition of the, that would really change when you convert it back to the SME definition, it would really change the meaning. So for engineers, this particular interpretation could lead to major problems. So for example, if two trucks ended up with the same identifier because there was no specification that it needed to be unique, I know this is a simple example, but it's a good one. So if the wrong truck could be sent for maintenance, could be sent off site, could be scheduled, and that's very expensive for our industrial organizations. So finally, I'll start to wrap up with some lessons learned from our ontology processes. The first that I've discussed a lot is to treat this translation as an iterative process. The second was to know that an SME definition is not the implication of a first order logic definition, but one plausible translation. We've learned to test our logic with edge cases, and our subject matter expert really taught us this because it uncovered a lot of problems in our first order logic with examples and data from the real world. And finally, showing your logic to others can help you ensure that others interpret your logic as you intend it to be interpreted. And having those direct English translations of first order logic can be really helpful for that. So the things I've gone through in this presentation is that first order logic helps people and machines to communicate. It assists in the interpretation of data. First order logic makes natural language definitions more precise and vice versa. And finally, less mistakes are made when translation is treated as a collaborative process. So just to wrap up, if you did want to read our blog, where there's a blog post where this presentation was inspired from, that's at ontologyexplained.com. And if you want to find out more about the Industrial Ontology Foundry, where many of these examples that I presented have derived from, then you can see their website too. And that's it. So I guess we'll leave questions for the rest of the session.
Thank you very much, Caitlin. Okay, we do have some questions on the chat room. I believe Ravi is first. Ravi? Go ahead, Ravi.
I just unmuted myself. I hope you can hear me.
Yes, we hear you.
Well, how do we go? Do we go by the speakers?
Yeah, ask the speakers.
Okay,
Please.
so the first speaker, you know, I was just implying that I hope you are not giving stricter definition of a hospital based on architecture alone. And I meant physical building architecture, because there could be concepts of hospitals such as mobile, tent-based, or advanced forward operations based for any project. So yes, what I liked in your talk also was that you believed in some drop-down functioning that you provided to guide the person to what attributes about a definition to pick up from the list.
Selja?
Yes. Yeah. Thank you for your comments. Yeah. No. So obviously the example I went through is just an example, and you wouldn't necessarily define all the classes in this exact specific way, all the hospital functions. And I don't know, so it would, like, the specific end result will totally depend on the ontology you have, on the existing classes, on the classes that are represented there, on which classes you want to add there. So it's all about the ontology design, which you would have to discuss with the team of ontologists and subject matter experts. This was just to illustrate kind of the method, the different steps that you would go through to create these templates that would then allow you to have more consistency in the definitions of your different classes. Yeah, I hope that's helpful.
Yes, thank you. I'll wait till everybody asks the first speaker, or do I ask second?
Go ahead, you can continue, Ravi.
I continue?
Yes.
Okay, so the second one is for Andrea, and I think she gave partial answer, and that was that semantics is implied in the slide that I mentioned, the slide number 9, I think. And you know, I like to contrast static depictions of things versus dynamic depictions. And when you talk of events and processes, you are obviously talking of dynamic situations. So in terms of semantic distance or richness measurement, how would you categorize these two types of ontology?
So, Ravi, I'm distinguishing between the definitions of things. And so you have events, or you have states. You have an event like this is a cooperative event. This is a competitive event. This is a meeting of the G9 or something like that. you have concepts like a meeting and things like that. And then you have instances of that and instances of your process, which can always, are always very variable. But once they've occurred, they're not dynamic anymore. You're recording history. Now, you can record history with some error. I mean, they always say history is written by the victors. So, you know, history even itself is not definitely truthful, but what you are defining, concepts of competition, concepts of violence, concepts of somebody saying something, concepts of meetings, those are definitional. And you have information related to those that varies from the definition all the way to the linguistic usage, verb net kind of thing, and how you put it together in a process or in a sequence. Every sequence does not have to be a process, is part of how somebody is relaying their information or telling their story. So for me, dynamic is the sequences, the connections that people make, and what's static is this definition. You have a definition of violence. Now, what someone might call violence will vary. Like somebody might say, oh, I don't think verbal abuse is violence. And another person would say, I think all abuses are kinds of violence. So those, maybe some of those things have to be resolved within understanding who is saying something and what they mean by the words that they use. But having the concrete definitions in your ontology, I think, are important.
Okay, I understood the trustworthiness of the person or persons or groups making certain statement enters in what you just mentioned. But is there any inherent difference in ontology creation based on these categories? For example, an event that starts by itself, some prompting event, trigger, or events that are more static?
Well, events are the things that happen, and you can say that one event caused another, or you can talk about processes that have a triggering event. You know, when an email comes in, then I open my email and I respond and stuff like that. So there are triggering starting events for a process. There could be component events in an event. You can always break something down to much finer granularity if you need to. I don't think they're, I don't think those are orthogonal concepts. I think that's all part of how you're thinking about an event or thinking about a process.
Thank you. Maybe John has a question.
Okay, well, I have enjoyed some of these discussions which emphasize the point that I've been mentioning all along, and that is that somehow we have to relate the natural language to first order logic, and that is the critical issue that we need to implement on our computers. And there's a huge amount of work that's been done with relating language to logic. And the thing is that that has to be the foundation for this, for all of our implementation for going forward. The underlying ontologies are going to be under the covers, and they have to be developed automatically by the computers. It is much, much easier for a computer to design or to implement an ontology that is completely consistent than for it to prove that some human-generated ontology is consistent. In general, proving consistency of a predefined set of definitions can be difficult or impossible. And it's always easier if the computer generates the ontology in such a way that it is guaranteed to be consistent. And as far as the semantic web notations, they're just, they're a 20-year-old garbage. They are old-fashioned, very clumsy and clunky, and the sooner we get rid of them, the better. But I recognize that we're not going to get rid of them immediately. They're going to be legacy technology that will survive for a long time, but I regard them at the level of TCP/IP. It would be impossible to do the internet if everybody had to communicate with TCP/IP. All that is under the covers, done automatically by the computer, and the same thing has to be done with the communication between natural language and the humans. Now, the major problem with language understanding is that there are huge numbers of ambiguities, and the best way to handle ambiguities is the way that people do it when they're talking among one another. They just ask a question. They just say, "Do you mean?" or "What's that?" or "Could you please restate that?" So the idea is that it's possible for the computer to recognize when it has a high degree of reliability in what it's interpreted, or when it's sort of on the edge and there are various uncertainties. And so the point is that whenever the computer interprets anything that the human says, it must always come back with an echo and say, "This is what I mean," and where it echoes back in its own terminology what it thinks the human said, and there's always going to be a dialogue. And another point is that intentionality is the most difficult thing of all. It's like understanding the point of a joke. Computers never, ever get the point of a joke. And also that can be hard for people, especially somebody who isn't familiar with the context or with, they can't always tell whether somebody is making a serious statement or a joke. And so it's important to be able to ask questions. And the two most important questions are how and why, because those are the ones that are the most likely to be misinterpreted by the computer. And so you always need to be able to ask a why question or a how question. And also the computer is very hard, it's very difficult for the computer to understand intentionality. And that's why the computer always has to be able to ask why. Why did you say that? What's the reason? What's the intention? What's the purpose? And all of these are technologies that have been implemented at small pieces at a time on various trial projects, and they're ripe for putting them together in a system in which you have really a good conversational dialogue between the computer and the human. And you should never have to take a whole document in English or any other language and translate that to logic. What you should be able to do is to have a dialogue where you're only processing sentences within the current context. And the humans can be those people such as the system engineer is a human, the knowledge engineer is a human, the domain experts are humans, and the naive user who's trying to use this stuff, they're all humans, and they all can understand one another when talking in their same natural language. But the point is you need to have the computer as part of the dialogue. So the computer will carry on a dialogue with the systems engineer and with the knowledge engineer and with the philosopher or linguist and with the naive user and discuss all of them. Language is the universal, natural language is universal. It's the only.
How do we get these to stop being so proprietary and actually shared with the public, these natural language understanding tools that people have been building, for these DARPA projects and so forth? I mean, because they do exist, like you just said, but people don't have access to them yet.
Of course not. So we have to make access. That's the point I'm trying to make. The number one goal of ontology is to make those systems accessible. That's essential.
I do think if Tim Berners-Lee would have said, we're going to be using something more expressive for our base language, I agree with you with that, then these tools would have been.
He most definitely did.
Yeah.
He said the swell language was a superset. In fact, common logic was designed according to Tim's specifications as a very general logic. He did not specify. He did not specify a specialized those teeny weeny specialized languages like ontology. That's like OWL. OWL is a disaster. Swell is common logic.
Yeah, but I mean, like, if everybody would have been working on reasoners to work with common logic rather than reasoners to be like unifying over RDF, that was just kind of silly. We would have actually had event calculus reasoners, situation calculus reasoners, things that would like merge common or CGIF together. You know, if we would have had, if those would have been the tools that were demanded to be built in the semantic web time, then we would have had those. But instead, people were building OWL tools, Sparkle servers.
That's
no, that's a very serious project. The problem is that the description logic people hijacked the project. And they destroyed Tim's vision by downsizing it to what they were doing. They were trying to push this description logic, which is a disaster. That was a disaster. They destroyed the semantic web by forcing people to use OWL.
Oh, but please, let's get back to the topic at hand. Would any of the panelists care to comment on this? Caitlin, for example?
I think that's a fantastic idea. From engineering, we have one problem, and that's that much of our natural language data, we don't have that much of it. We have unstructured work order records where technicians enter a short text description of the work order record. We occasionally have technicians who write things on, maintenance procedures about the health of the equipment, but we don't have that much natural language data that we can really run lots of machine learning over it. So I was wondering, how you'd propose to deal with low resource domains like this.
I'll talk about that next week. The point is, 20 years ago, my colleague Aaron Majumdar had implemented an excellent tool for processing email specifications written by humans for other humans and relating them to software implemented in COBOL and IBM's job control language, and doing the language relating natural language to the formalisms automatically using a level of first order logic as the intermediate. And that was 20 years ago. And I'll talk about that next week.
Okay, cool. I'll have to listen in.
Anyone else on the panel care to comment?
I would like to say I've successfully used OWL too. I've successfully used rules in Swirl, and you make use of the tools that you have and you expand where you need to, and combining ontologies underneath to provide semantic reasoning. Having ontologies as an end goal, I don't think is a very good idea. They're a tool to accomplish something, and there are lots of tools available, and for different people, different tools work. And so I would counter by saying I don't think the world is as terrible as John thinks.
No, I agree with Andrea. I agree totally with Andrea. For the rule, somebody with the ability that Andrea has can deal with these things. On the other hand, 99.9% of the people in the world can't do that, and that's what the problem is.
Yeah, and I think if that's what you're saying, John, I agree with that, and that's kind of why I'm working so hard to try to get people to think about why you define and how you use an ontology differently. It is not an end goal. I mean, it's a tool that you use to solve other problems.
So something that you showed, Andrea, was some like narrative, like event calculus sort of in these frames on your slides. And, you know, the most difficult part is then connecting those frames. You know, I guess you would only, how would you get a link between this event stage in a narrative to this next event stage? Do you end up having to create a B node, or is it?
And not necessarily. I mean, you can, when somebody's relating, you know, their life history or something, they usually give you in the dialogue clues about, you know, when I was a little girl, but when I was in high school, and then in my first job or my fifth job or something. And so you have kind of, the context gives you some of the clues. You can, without knowing exact dates, you can create a, this happened, then that happened, you know, you kind of a sequence of nexts. And
yeah,
and in the analysis, some of the things that John said in the work that I'm doing is very true, because when you don't know, and the computer does not know sometimes, and there's no clue, you go, does this make sense to a person? Or you can say, here's an inconsistency I found. Can you help resolve this? Most of my current work, though, kind of requires that you analyze the narrative, and at the time you're getting the narrative, you're actually the computer's asking some questions of people, or the interviewer is asking questions of people.
yeah. So you get so you do build the sequence in at least, if there is something.
Yeah, you pretty much have to, and my work kind of relies on those clues.
Right. And by the way, I fully agree with the idea of using event calculus or Petri nets or lots of other kinds of things, but the communication between event calculus and Petri nets and your databases is all going to be done via first order logic. You can specify a Petri net in first order logic. You can specify your event calculus in FOL. So the FOL is sort of, that's
Definitely
the base level, and you're going to use all kinds of other systems for doing your reasoning for special cases.
Yeah, and I use programming for my first order logic.
Oh, of course, of course. In fact, first order, you can specify any programming language in first order logic, and that's perfectly fine.
So Andrea, do you use a bit of Prolog or Java, or what ends up being your language of choice in these
Prolog
cases?
is also very important, but Prolog can take your FOL inputs and process them. In fact, Prolog was designed as a tool for processing natural language. That was the original goal. The original application of Prolog was processing natural language.
It also just makes a great reasoner language too, for canonicalizing first order logic into smaller entailments, into conjunctive moral form, and etc.
Absolutely, absolutely.
So I just want to say that I use Python and I use Stardog. So I use Stardog to do reasoning and consistency analysis and all of those things underneath. And I use Python for its natural language processing, natural language understanding, and open source libraries. So has things like Spacey and stuff like that are amazing.
Well, that's fine. That's fine. And again, those are tools that can be used by the 0.01% of the people in the world. And the thing is that everybody uses some version of natural language, and that's going to be the goal if we want to communicate with everybody.
There was a question from Chirp. I'm not sure I'm pronouncing that right. Asking about temporal geometries.
Yeah, I tried to answer that, Ken, in the chat. So And I think he had to leave.
Yeah, he left. Could you elaborate a little more on that?
Well, I was trying, there's kind of two theories of, or there's two approaches here. My approach is a far more modular one, and to interject the components that you need for your domain. Having a concept of time and having your top level ontology tell you what the time is, or time geometries or spatial geometries or whatever, I think is problematic, because it depends on the domain. It depends on what problem you're trying to solve. So clearly spatiotemporal things are important in any kind of narrative analysis, event analysis, any kind of natural language understanding. You have to know the context. Time can, I more go with the, as Doug was talking about, I more go with the event calculus kind of approach. James Allen's, 13 different kinds of relationships, et cetera, et cetera. But I think a key to all of it is understanding your context, which is also your time and your space. So I wasn't sure exactly what Joe was trying to get at, but there is no real analysis without 4 dimensions.
Great, great. Thanks. Mark Underwood, I believe, had a comment or question. You still there, Mark? It sounds like he isn't. Okay, well, we've come to the end of our hour and a half. So I want to thank all of our panelists for a fantastic session today and a wonderful discussion. We're going to be continuing at least some of these next week, when John and Aaron are going to be speaking. So I would hope everyone would come next week for what could be a really interesting presentation by both of them. I don't believe Aaron has ever been speaking at the summit. Is that right, John?
No, he hasn't. He attended one of the sessions where we had in person, at least. This was, I think about a year and a half ago, before all the COVID things started.
Yeah, so it'd be great to have him.
Yeah.
I think I'm really looking forward to that. I hope everyone else can attend. And so with that, I will adjourn the formal session.
John, Ken, you want to thank Alex for his efforts?
Oh, and Alex, yes, thank you for putting this whole panel together.
Thank you.
Thanks, that was great.